We are recording.
This is my forms of internal corrosion PowerPoint. I did mine on the chemical forms of internal corrosion. The first one is going to be ammonia. Ammonia causes stress corrosion, cracking, and is very acidic. Corrosion from ammonia typically happens in pipe and storage tanks where ammonia is present. Here's some pictures. Supporting environments are going to be storage tanks, piping and equipment, and any storage unit for ammonia. Susceptible metals and alloys are going to be aluminum, copper, bronze, zinc, and iron. Corrosion factors, different temperature ranges for different metals. Ammonia concentration, air pollution. High temperature can cause gaseous ammonia to form, exerting more pressure on the inner walls of the tank or pipe, causing stress corrosion, cracking or accelerating. Testing and monitoring methods. Hanner electrochemical device, ANISE, SC sensors, radiographic testing, frequent inspections of material in contact with ammonia. Corrosion control. Adding chrome to the affected area acts as an inhibitor. Sodium nitride can be used as an oxygen scavenger to minimize impurities in the ammonia. Mild steels and stainless steels are resistant to ammonia corrosion under certain environments. The next one's going to be ammonium bisulfide and ammonium hydrosulfide. They're kind of the same thing. It's just hydrogen and then two sulfide ions. Ammonium bisulfide corrosion is an aggressive corrosion occurring in several refinery units, including hydro treaters. Here's some pictures. Supporting environments, refinery units, hydro treating units, piping elbows, inlet header box of the reactor, effluent F/F exchangers. Susceptible metals and alloys. Carbon steel is the least resistant metal. Stainless steels, duplex stainless steels, aluminum alloys, and nickel-based alloys are more resistant but still susceptible. Corrosion factors are going to be velocity, temperature, NH4S concentration, dew point control, pH, NH3 and H2S, and HCl partial pressure. Corrosion control. Regulate and monitor temperature, regulate and monitor partial pressure, reduce concentration of ammonium bisulfide by use of neutralizers and inhibitors. Carbon dioxide is going to be the next one. Corrosion from carbon dioxide happens when CO2 dissolves in water and forms carbonic acid. The acid can induce general corrosion and pitting, corrosion by lowering the pH, sometimes called sweet corrosion. Supporting environments, refinery steam condensate systems, hydrogen plants, vapor recovery section of catalytic cracking units, areas where water condenses, areas where CO2 is dissolved in water. Susceptible materials are going to be steel, such as in piping and equipment, and iron, such as in piping and equipment. Rules of thumb. 15 psi partial pressure or lower in equipment helps to inhibit this type of corrosion. Corrosion factors are going to be material type, CO2 concentration, temperature, pH, partial pressure. Decrease in pH results, increase in corrosion rate, increase in flow rate results are also increased with corrosion rates. There's a cell mechanism. Testing and monitoring methods. Electrochemical tests, lab tests. There's chemical test kits, predictive models like mechanistic and software. Corrosion coupons, intelligent pigs, corrosion control. Membrane contactors can be used to remove CO2 from the system using inhibitors as well, continuous injection into pipeline, sufficient monitoring and inspection. The next one's going to be caustic embrittlement. Caustic embrittlement is a form of stress corrosion cracking that is caused by sodium hydroxide being introduced into stressed metals. Here's the pictures. Supporting environments are going to be caustic embrittlement happens primarily in boilers. It can occur in containers that have heavy sodium hydroxide, are under high pressure and high temperature. It also can happen in high alkaline environments. Susceptible materials are going to be low alloy steel and carbon steel. Corrosion factors are going to be high stress. Structure contains free sodium hydroxide, temperature range of 200 degrees to 300 degrees Fahrenheit, and high pressure. Testing and monitoring methods: acoustic emission testing, magnetic particle testing, ultrasonic testing, and wet fluorescent magnetic particle testing. Corrosion control, stress control, temperature control, avoid alkali metals, adding sodium phosphate as a softening agent. Next one's going to be chlorine. Chlorine is a very strong oxidizing agent for all metallic and organic species present in the system. Chlorine corrosion causes localized corrosion in the form of pitting and chloride stress corrosion cracking. Here's some pictures. Supporting environments are going to be treating cooling water, treating wastewater, high temperature and pressure storage tanks where chlorine can be contaminated. Susceptible materials are going to be carbon steel, cast iron, bronze, titanium, and stainless steel. Rules of thumb: here's the equation for this type of corrosion. Corrosion factors are going to be, if the pH is below 7, high corrosion rates will occur when chlorine is present. Above 230 degrees Fahrenheit, corrosion rates are accelerated, and from there on up. The corrosion mechanism, for example, this is the reaction with iron. Here's that equation. Ferric hydroxide precipitates out and is deposited on the walls of the piping material. Testing and monitoring methods: monitoring, MagnaFlex, spot check, SK816 penetrant inspection kit. UltraCore uses ultrasonic technology. Testing: DPD detects chlorine in the system. Corrosion control: sodium thiosulfate can be used to neutralize the chlorine in the system. Monitoring chlorine amount in the system. Use of low carbon steels with equipment being used in contact with chlorine. Next one's going to be hydrogen sulfide, H2S. Acid attack that results from the biological conversion of hydrogen sulfide gas to sulfuric acid when moisture is present. A direct chemical reaction with metals, such as copper, irons, and silver with hydrogen sulfide gas. Pictures. Supporting environments are going to be anything used to transport or treat wastewater, water that contains sulfate, wastewater pipelines, or wastewater treatment plants. Susceptible materials are going to be copper, iron, silver, steel, cast iron, and carbon steel. Rules of thumb: 5 things must be present in order for hydrogen sulfide corrosion to occur. Sulfate, anaerobic bacteria, aerobic bacteria, oxygen, and water or hydrogen. Corrosion factors: moisture on the affected material, low levels of dissolved oxygen, sulfide in wastewater, and release of hydrogen sulfide gas from solution. Temperature, materials tolerance of sulfuric acid. Test and monitoring methods: atmospheric H2S tests, visual inspection, ultrasonic inspection, and hydrogen sulfide testing. Corrosion control, ventilation, purging with clean air, use of corrosion-resistant materials and clip coatings, preventative maintenance, reduce dissolved sulfide content with addition of chemicals like hydrogen peroxide, chlorine, potassium permanganate, and sodium hydroxide. Hypochlorite is going to be the next one. Hypochlorite ions react with metals to create corrosion cells, such as pitting or cracks. At high temperatures and pressure, hypochlorite ions can induce stress corrosion cracking. Here's some pictures. Supporting environments are going to be piping and equipment where hypochlorite is present. Susceptible materials are going to be stainless steel and carbon steel. Rules of thumb: aluminum is very weak to hypochlorite because of its high pH. Visual clues may occur, such as pitting. Corrosion factors: concentration of hypochlorite, temperature, pressure, presence of other chemicals. Testing the monitoring methods: force flow hypotrack chemical tester, MDPI wireless sensor, chemical sensor. Corrosion control: using more resistant materials such as fiberglass reinforced plastic, monitoring concentration of hypochlorite ions. Next one's going to be oxygen. Oxygen is a cathodic depolarizer that reacts with and removes hydrogen from the cathode during electrochemical corrosion, thereby permitting corrosion attack to continue. Here's some pictures. Supporting environments could be pipelines, boilers, oil and gas wells, or any aqueous environment. Susceptible materials are going to be cast iron, carbon steel, bronze, zinc, and brass. Rules of thumb: formula for the reaction with iron is going to be Fe plus FO2 plus H2O, FeOH2. Stainless steel and titanium are very weak. Corrosion factors: temperature increases rate of chemical reaction, lower pH level increases corrosiveness, rate that fresh water is being introduced to the cell. Testing and monitoring methods: boilers use trace dissolved oxygen measuring sensors, electrochemical devices, and acoustic emissions. Corrosion control: deaerating heaters and vacuum deaerators, oxygen scavengers, sodium sulfide, hydrazine, sodium bisulfite, pH control, temperature, and use of higher alloy steels. Yeah.